Welcome to 6.3. Today we're going to generalize what we did last time. And so in order to do that, I'm going to start with a review problem, but I'm going to change up the letters a little bit. So suppose we have two vectors, y and u in Rn. This is like before, but I'm going to call the span of u w instead of L. So last time I said L was the line spanned by u, and we're going to let y hat be the projection onto W of y, and that's the same as last time. I would have called that the projection onto L of y. We can write y as y hat plus z, and so let's review those formulas. Y hat is y dot u over u dot u, u. And that, last time we said that lies on the line L, or it's in the direction of u. You can see this vector is parallel to u, but we're going to say today that this is in W. W is the space spanned by u, so that's certainly true. And z is y minus y hat. Now that was orthogonal to y hat, so today we're going to say that's in W perp. So for example, let's do this problem here. Here we've got y and u, and w is the span of u. Write y as the sum of two vectors with one in w, and then find the distance from y to w. So first we want y hat. Y hat is y dot u over u dot u, u, which is 10, and u dot u is 16 plus 4, which is 20, and that's times u. And u is, I'm switching to linear format here, -4, comma 2. So that's 1/2 of -4, which is -2, and then +1. So there's y. Z is y minus y hat, which is 1/7 minus -2, 1, which is 3, 6. So y is y hat plus z, -2, 1 plus 3, 6. This is my y hat, and that's my z. Distance, so first let's do the safety check. The safety check is 1, is y really equal to y hat plus z? So if we add these two vectors together, we get 1/7, which is y, so yes. And 2, y hat dot z should be 0. And is that true? -6 plus 6 is 0? Yes, that's true. So we did this correctly. And then finally, what is the distance from y to w? The distance is the length of z, which is square root of 45. So the computations haven't changed. I'm just changing the letters a little bit, as I said, to make this theorem more like the ODT, which is the generalization. So now W doesn't have to just be a line. It doesn't have to be this space spanned by a single vector u. W can be any subspace of Rn. And the theorem is that each y in Rn can be written uniquely as y hat plus z. And the formulas for y hat and z, if you happen to have an orthogonal basis for w, is y hat equal projection onto w of y, and then this formula. Now this is the same formula that we learned last time. This is the formula from theorem 5 last time, so that should look familiar to you. And then z is y minus y hat. And just a couple of comments here. I've got a picture. I'm showing W as a plane, Y. The projection of Y onto W lives in W, so that's Y hat. And then Z is over here. Z is in W perp, so that'll be perpendicular to Y hat. Y hat is called the orthogonal projection of Y onto W. In the next section, Gram-Schmidt, we show that every non-zero subspace has an orthogonal basis, so it's not too much to ask that you have one. And thirdly, this one makes good sense. If y is already in W, then when you project y onto W, you get y itself. So y hat is equal to y in the event that y is already in W. So let's do an example. So now we've got W is the span of U1 and U2. Suppose y is 0, 3, 10. Verify that we can use the ODT. Is U1, U2 orthogonal? U1 dot U2 is indeed 0. So we can use the ODT. Find the orthogonal projection of y onto W. So y hat, that's what's being asked for, is y dot u1, u1 dot u1, u1, plus y dot u2, u2 dot u2, u2. Okay, and so that is, I'm going to switch over to linear format. Y dot u1 is 10, and then u1 dot u1 is 10, so 10 over 10 u1, and then y dot u2 is 3, that's a 1 there, 3 over u2 dot u2 is 1, so I want u1 plus 3 u2, so u1 is 301, and then I want 3 times u2, which is 0, 1, 0, and so that gives me 3, 3, 1. So there's y hat. Write y as the sum of a vector in W and one in W perp. So I want the decomposition. I want y equals y hat plus z. So first I need to find z. Z is y minus y hat. Okay, and y was 0, 3, 10. Y hat is 3, 3, 1. So that gives me negative 3, comma, 0, comma, 9. So y is equal to y hat, which is 3, 3, 1, plus z, which is negative 3, 0, 9. Okay, let's do our safety check. 1, is y really equal to y hat plus z? So coming over here, if I add, I get 0, 3, 10. That's y. 2, is y hat dot z equal to 0? Yes. Okay, so since this decomposition is unique, if those two things check, you did it right. And finally, what is the distance from y to w? We want the length of z, that's a z there, which is the square root of 9 plus 81, which is the square root of 90, or you could write 3 root 10. Okay, so the best approximation theorem justifies this word distance. When we say what is the distance from y to w, the best approximation theorem says that y hat really is the closest vector in W to y. So that's all it says in English. Y hat is the closest point in W to y. And then this just makes that explicit mathematically, that the distance between y and y hat is going to be less than the distance between y and v for any other v in W that's not equal to y hat. And so I have a proof at the end, but here's a picture. If you're living in W and you want to be close to y, then you want to be y hat. This vector here is the closest one to y in W. Any other vector, this distance is going to be longer than this distance. And so we truly can say that the distance from y to w is the length of y minus y hat. That's the length of z, because y minus y hat is what we're calling z. All right, for example, find the closest point in w, and w is the span of u1 and u2, to the vector y, and then find the distance from y to w. So can we use the ODT? We need to check that u1 dot u2 is 0, and it is, so we can. What is y hat? Y hat is going to be the closest point, so that's the vector we want, and the formula is y dot u1, u1 dot u1, u1, plus y dot u2, u2 dot u2, u2, which is equal to, here we go, y dot u1 is 6, u1 dot u1 is 2, u1, and then plus y dot u2 is negative 2, u2 dot u2 is 2, u2. So I'm going to have 3u1, and u1 is 1, 1, 0, 0, and then minus u2, and u2 is 0, 0, 1, 1. So that's 3, 3, negative 1, negative 1. So that answers find the closest point in W to Y. And then the distance, we want the length of Z. So first we have to find Z. z is y minus y hat. Y is 240, negative 2. And y hat is 3, 3, negative 1, negative 1. And so let's see what that gives us. It gives us negative 1, and then 1, and then positive 1 again, and then negative 1. So that's z. And so the distance is the length of z, which is the square root of 4, which is 2. All right, so this is a pretty short video, but I want to end it with a comment on your homeworks. These come from homework problems here. And it's just the verbiage that I want to talk about. It's not really the computations. Find the distance from y to w, given that the closest point to y in w is y hat. So they give you a vector y, u1 and u2, w is the span of those two vectors, and a y hat. So they're giving you more information than you need. You don't need u1 and u2 because they've already found y hat for you. So all you have to do is first compute z, which is y minus y hat, which is going to be 4, 4, and then 4, and then 4. So there's z, and you just have to compute the length of z, which is the square root of 4 squared is 16, and I have 4 of those. I'm going to multiply there. Square root of 16 is 4. Square root of 4 is 2. 2 times 4 is 8. So the problem's easier than it looks. And then this one, it's a little confusing because they change up the letters on you. So the question is, find the best approximation to z by vectors of the form c1v1 plus c2v2. So what is being asked for? Well, let's let w equal the span of v1 and v2. And note, v1 and v2 are orthogonal, I believe. Yeah, v1 and v2 are orthogonal. And if you want the best approximation to z by vectors in w, so if they're in this, if they're of this form, that means they're in w. What is being asked for is z hat. So usually we think of z as in the orthogonal complement, but here we want the projection of z onto w. So we want z hat equal the projection of z onto w. And I'll just leave it for you to show that if you do that computation, ... you should get 2/3 v1 and then 0 v2. So you'll get the vector 4/3, 0, negative 2/3, negative 4/3. And that would be the answer there. All right, and that is the end of this section.